Everybody is familiar with Pythagoras theorem, but there is a problem. In this video, I'm going to show you how Pythagoreans misled Fermat in his formulation of the Fermat's last theorem. Follow me in this video. If you find this video very useful, don't hesitate to subscribe to my channel. See you in the video. All right, you are welcome, guys. In this video, I want to show you how Pythagoreans misled Fermat in the formulation of the Fermat's last problem. So, as you can see, we are going to start from the Pythagoras theorem itself. We're going to start from the Pythagoras theorem. So you all understand what the Pythagoras theorem is all about. It's actually talking about the size of the right angle triangle. And we have that the theorem is actually basically the relationship between the right angled triangle. Okay, so it stated that given this particular shape, which is a right angled triangle, then given z here, which is the longest side of this right angled triangle, then you have this to be true. Okay, that is x squared, the square of this, plus the square of this gives you the square of the longest side, which we have in this is the general Pythagorean theorem. Okay, but there is something we want to note about this theorem, which is very fundamental to understanding this particular equation and the subsequent equation or work that's going to be built on top of this equation. Okay, so and before we move on, I want us to look critically at this equation. What is it talking about? It is actually talking about the length of the side of the triangle. It's talking about the side of the triangle, and we have three sides there, and there is a relationship between those three sides. It is that relationship that is captured in the Pythagorean theorem. So now, what we have here, the x, the y, and the z, is a variable which represents the length of the triangle, the length of the size of the triangle. Okay, so basically, by definition, this actually reads the length multiplied by itself, that is this x squared, okay, plus the length y multiplied by itself, okay, we give you the length z, which is this place multiplied by itself. So we are talking about length multiplying itself. Length multiplying itself, don't forget. And you will recall that length, as we have it here, is not a discrete variable. What do I mean by that? It is not something that you can count. Like, for instance, if it is you are talking about population of a certain object. For instance, you have birds flying on the sky. Then you can count the number of these birds you have there. If it is a ram, for instance, a ram, you can count stones. There are some things you can count, like normal counting, physical counting. 1, 2, 3. So, but such is not so with what we call length, with the concept of length. You can't count length. The only thing you can do with length is measure. You can measure the size of the length. Okay, so length in that regard is not a discrete object. Okay, so and then secondly, in that, if that is the case, we will accept, we will agree that the length object belongs to the real set, the real line, and not Z. So X, which is this place, the length of this triangle does not belong to Z. That is, they are not integers. They are not integers. The value of this X, Y, Z, the length of the sides of the triangle, are not integers. You should take that into consideration. You should take note of that. So as we go on in our explanation, you will see why that is very, very important. We are not dealing with an integer variable. We are dealing with a variable that is continuous, which cannot be counted. Rather, it can only be measured. X, Y, and Z represent the sides of the right angle triangle. Okay, so and they are not a discrete variable, they are continuous variable. So they do not belong to Z. Okay, so they belong to real set, not Z. Okay, so now Pythagoreans try to prove a theorem. Now this is the method. He translates, he built a square, 3 squares around the triangle, the rectangle triangle we are talking about, and then he go on to prove that the area of Y and the area of X, that's if you add them together, should give you the area which is generated by the length of the hypotenuse. This area, if you add the area of this shape, this square, to the area of this square, it should give you the area of this entire square. That's if you add the area of this square to the area of this square, it should give you the area of this square. That's how he tried to prove. Okay, so which means it can actually be represented this way. So what is the issue here? That's according to Pythagoreans, he meant that the area of the length generated by Y plus the area that is generated by X will give you the area that is generated by the length Z. Okay, so now the fundamental problem here is that Pythagoreans deploy a 2D object because area, this square you are seeing here, is 2-dimensional. Okay, and this is a separate concept on its own. Okay, so but he went on to use this concept to conclude on the behavior of a line, which is a 1-dimensional object. And this process is strictly inappropriate because square on its own, the relationship between squares on its own, they are fundamentally different from a line. A line is a 1-dimensional object, while squares have they are 2-dimensional objects. Okay, so and to me, this proof actually led to another statement that needs proof on its own. The question is this area equal to this area plus this area? That is another thing entirely. Okay, and another question is it true for all right angle triangle irrespective of the size? So is Pythagoreans saying that this area is a result of the sum of this area plus this area for all right angle triangle? Okay, so he was talking in his proof, he was talking about the area generated by the lines. the area generated by the lines. And coincidentally, finding a supposed solution in Z is what actually led to the error of discretizing the areas and others, like volume. Trying to find, because now, let us go back here now, S squared. Okay, S squared does not refer to area. There is a difference of, there is an error of definition here. S squared, you have it like this, S squared, okay, this can have two meaning. It means x being variable multiplied by itself, and it can also mean area, okay. But now, because we have S squared, we automatically assuming that this S squared means area is the error in the whole process. It is what actually led to the error, because x squared might not necessarily mean the area, it might not necessarily stand for area. What if in some occasion the S can stand for temperature? What if you have the square of the temperature how will you interpret it? Okay, so it is erroneous to take S squared, anything squared, to mean an area. Okay, so that is the second error there. Solving for that equation, if you solve for Pythagoras equation, you will find that 3, 4, 5, for instance, is an example of a solution that can solve that problem. Then we have 5, 12, and 13, which is another solution. We have several solutions like that. Okay, and this is where it is getting very interesting. Look at this. This is Z, which is the set of integers. Okay, and these are solutions of Pythagoreans theorem, 3, 4, 5, for instance. So the existence of these solutions led mathematicians to the holy grail of finding same solution for the same equation of higher order, because the mathematicians think that because 3, 4, 5, 5, 12, 13, and a whole lot of other solutions which they think belongs to Z, okay, which they think belongs to Z, might actually exist also for other higher equation of the same form. So now the question is 9, 12, 16, for instance, which is one of the solutions of the Pythagorean theorem. Are these values areas? The answer is no. They are not area. They do not actually represent areas. Okay, so and if there exist solutions in Z which solves the relationship given by the Pythagorean theorem, this which you have here, which solves this Pythagorean theorem, then there could be a solution in integers. There could be an integer solution that will solve for x is power 3 plus y is power 3 equals to 0 is power 3. It's because if you have an integer, you have a solution in Z which is an integer. That means you have an integer solution that can solve this one, this s squared, okay, plus y squared is equal to this squared. Then mathematicians think that there should be a solution too in Z, which is an integer that will solve x raised to power 3 plus y raised to power 3 is equal to 0 raised to power 3. It is the same form, but just that the power increases by 1. Okay? And they even reason further to think that there could be solutions in Z, that there could be an integer which could solve the general form of this equation. That's x raised to power n plus y raised to power n is equal to 0 raised to power n. Okay, so that is the where mathematicians now begin to reason generally. Okay, and that was what led to Fermat's theorem. We are going to see in a while. So then the true point here is that Pythagorean's theorem itself has no solution in Z. It has no solution in Z. Don't forget, if we go back, we see that this x, y, and z does not belong to Z because they are not discrete. They are uncountable. It can only be measured. Okay, you cannot count them. Cannot count length. You can only measure it. So now what happens there is that the three which we have, for instance here, this solution, let us take this for example, 3, 4, 5 does not actually belong to Z. If we solve Pythagoras theorem, they are not an integer. So if they are not an integer, what are they? They belong to real. And in that case, the 3 we see is not actually 3. This is the actual solution. 3.0, 4.0, 5.0. These are the numbers that actually solve that Pythagoras theorem. And all other solutions like 5, 12, 13, and the rest of the solutions set of the Pythagoras theorem are not whole numbers. They are 5.0, for instance, 12.0, 13.0, rather than 5, 12, and 13. There is a difference in my next video. I'm going to explain what the difference between 3 and 3.0. There is a big difference there between 3 and 3.0. Okay, so in my next video, watch out for my next video. I'm going to explain it in detail why 3 is not equal to 3.0. They are not the same thing. Okay, so and the solution you see, which is 3, 4, 5, they are actually 3.0, 4.0, and 5.0. And they belong to R, which is the set of real numbers, not Z. They do not belong to Z. They are not integers. Okay, so now, because mathematicians believe that the solution they have for as the solution of the so-called Pythagoras theorem, they believe it belongs to integer. So after a long search for the same integer solution to this general equation, which resembles Pythagoras theorem, they now find out that it's not possible. It's an holy grail. That was why Fermat proposed that this general equation, x raised to power n plus y raised to power n equals 0 raised to power n, has no solution in integer z for n greater than 3. For n greater than, that is the power here. Talking about the power being greater than or is equal to 3. Is greater than or equal to 3. Okay, so if we try to picture this particular equation for n is equal to 3, we will have this. We're going to have this figure, this shape here. Just like we try to use square, just thinking in Pythagorean term, using square to represent the size. Then for n is equal to 3, for this particular one, x equals to 3, and let us take x is power 3, y is power 3, z is power 3 to represent volume of a cube. Let's take them to be volume of a cube. So if we arrange it this way, you can see even from here that it is not possible to have 3 cubes in such a way that the volume of this plus the volume of this cube will give you the volume of this cube. It's not even possible. If you look at the arrangement of this figure here, this diagram, you see that it is not possible to use the 3 cube to create a right angled triangular prism. If you look at the back, you see that it cannot align with itself. The front align, but the back cannot align with itself. So which means it is not possible. It is not possible to have 3 cubes that will be used to construct a triangular prism. So which means this equation has no solution in Z. But the purpose of this video is to bring your attention to the Fermat's last theorem. Why did Fermat reason that this has no solution in Z only for n greater than or is equal to 3? The question is, does this equation has a solution in integer, an integer solution for n is equal to 2? Because Fermat is talking about n greater than or is equal to 3 here. That's 3 and above. Fermat is saying that if n is equal to 3 and above, then this equation has no solution it has no integer solution. But the question is, does it have integer solution in Z for n equals to 2 and 1? The answer is no. So Fermat was being misled by thinking that x raised to power 2 plus y raised to power 2 equals to 0 plus 2 has an integer solution in the first place. Okay, so which we've already seen that it is not so. Saying that Pythagorean's theorem has an integer solution is misrepresenting the object that we have in the equation in the first place.